Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the nature of oxygen atom, and yesterday we have discussed about the nature of oxygen atom. Ephedrine on benzylation form a dibenzoyl derivative, indicating that oxygen atom is present as hydroxyl OH group because one benzoyl group is introduced at NH group while the other at OH group. So in that way we have seen then ephedrine on oxidation with K2Cr2O7 in presence of dilute H2SO4 furnished a ketone with same number of carbon atom, and therefore ephedrine contain a secondary alcoholic OH group. So in exam 1 mark question may appear like this: how will you prove the presence of secondary alcoholic group in ephedrine? So how will you prove? Here very simple. When ephedrine treated with K2Cr2O7 in presence of dilute H2SO4 gives ketone, that clearly indicate that ephedrine contains secondary alcoholic group. That's it. So this is the way. Then now the next point we are going to discuss today is the nature of carbon skeleton. What kind of the carbon skeleton, carbon framework present in the ephedrine, that we are trying to find out. So let's listen. First one, ephedrine on. First point here, ephedrine on oxidation with potassium permanganate. Ephedrine on oxidation with KMnO4 gives benzoic acid. Gives benzoic acid. That's it. Look at, very clean and very simple. So as we know that the molecular formula of ephedrine C10H15NO, right? This is the structure of ephedrine, and that will be treated with KMnO4, potassium permanganate. It gives or it produce or it form HOOC, that is a benzoic acid. This is a, as we know that this is a benzoic acid, and this will be the ephedrine and gives as a benzoic acid. And formation of benzoic acid proves that ephedrine might contain a benzene ring with a side chain containing secondary nitrogen and secondary alcoholic OH group, and therefore partial structure of ephedrine becomes, and therefore partial structure of ephedrine becomes, so we know that there is a benzene ring, right? This is a benzene ring, and where you C2H4 is a side chain, and now here as we know that there is a NHCS3 group, as we know that. Another one, there is a CHOH. This is a partial structure of ephedrine becomes benzene ring. This is a side chain, we don't know what is that. Then NHCS3 and CHOH. This type of the information we got over here. And now next point we are going to discuss the fifth one, nature of side chain. What type of the side chain this one is present here, that we are discussing right now. So let us see the point number 5 we are discussing over here. So let's see what is that point, that is a nature of side chain. Fifth one is a nature of side chain. That is a point of discussion. Right now we are discussing the two possible structure of side chain in ephedrine may be as follows. Let us see over here. Let us see here C6H5, that is a phenyl ring, then CH-OH, then CH2, NH, CH3. This will be the structure number first. Another structure we can write C6H5, CH-OH, then CH, then NH, CH3, and there just CH3. This is a structure number second. Observe these two structure carefully. Now tell me how many chiral center present in the structure number first. Look at here. Chiral center or the chiral carbon or the asymmetric carbon atom means the carbon atom carries 4 different group is known as chiral carbon atom or asymmetric carbon atom. If you observe this structure carefully, you will find here, and that chiral center is always shown by asterisk, that is a star like this. This is a mark. It indicates there is a chiral carbon. Look at here. This carbon atom has 4 different group. One is a phenyl group, hydroxyl group, hydrogen atom, and this big group, right? So that is a secondary group. Now if you observe structure number second, can you tell me how many number of chiral center present here? Here there are 2 chiral center. Look at here is a 1 chiral center. This one is again second chiral center. There are the 2 chiral centers are present over there. Now these are the 2 possible structure for ephedrine. Out of these structure, which will be the correct structure for ephedrine, that we are trying to find out. When ephedrine is heated with HCl, it undergoes hydramine fission to form propanophenone methylamine, and these fraction are probably possible only with structure second, and therefore now when if you heat the compound with hydrochloric acid concentrated HCl, what it gives? This gives the fraction. What kind of the fraction you get here? C6H5, then C double bond O, CH, then CH3, CH2, and another one is CH3 and NH2. These are the 2 fraction we are getting, or 2 product, formation of the 2 product. One is called as a propanophenone. This is called as a propanophenone, and this we know that methylamine. You can call it as a methylamine. This is a 2 compound which is given by structure only second, and that proves that the ephedrine has, this is the correct structure for ephedrine, and it is not the structure for ephedrine. Why? This structure number first is not for ephedrine. The reason behind it, if you treat this compound, if you heat this compound with concentrated HCl, it does not produce propanophenone as well as methylamine, and therefore there is no possibility of the structure of the ephedrine. That's this. And structure first cannot give propinophenone after hydrazamine fission, and hence structure second is the correct structure for ephedrine. Understood this? Structure first cannot give propinophenone and methylamine after hydramine fission, and hence structure second is the correct structure for ephedrine. Let us see the last point, support for structure second. So last and the sixth point we are discussing over here is which one? This one. Now let us discuss that point over here. Point number 6, that is a support for structure second. Support for structure second. Support for structure second over here. Now the structure second is supported by the fact that ephedrine, when subjected to Hofmann exhaustive methylation, yields 1,2-methyl-phenyl ethoxide, and thus structure second is more probable structure for ephedrine. So that is the thing. Let us see over here. Let's consider here C6H5, then CH-OH, CH-NH-CH3, and one methyl group over here. If you treat this compound with Hofmann exhaustive methylation, that is methyl iodide, right? Methyl iodide in presence of Ag2O, moist Ag2O, what it gives? It produces C6H5 CH-OH, OH I am writing here like the for sake of convenience, then CH-N, then CH3 thrice positive charge over there, CH3, then there will be a this type of the epoxide forms over there. Hit it, minus water molecule, you will get here C6H5, then CH, that is the epoxide over there, then CH3, and side product will be N, then CH3 thrice. That is a trimethylamine we are getting, and this one is a 1,2-methyl-phenyl epoxide. 1,2-methyl-phenyl epoxide, that is the product we are getting over here, and that clearly indicates that the structure second is further supported by the optical activity. Structure first contains only one chiral center. The replacement of OH group in structure first by hydrogen is the formation of an optically inactive compound. On the other hand, structure second contains two chiral center asymmetric carbon atom. The replacement of OH group in structure second by H yields optically active compound. Experimentally, it has been found that when this replacement is effected in minus ephedrine, the product deoxyephedrine is optically active, and this reveals that structure second is the correct structure for ephedrine and has been confirmed by its synthesis. Let us see the last point of this is a synthesis, that is a seventh point which we are going to discuss over here. Now is a point number 7 here. 7, synthesis or this synthesis first time is done by scientists, that is the synthesis of ephedrine. Synthesis of ephedrine. Synthesis of ephedrine, and this synthesis is done by first time in the laboratory. The name of that scientist is given to that synthesis, which is known as a Nagai synthesis. That is, first one is a Nagai synthesis. Nagai synthesis, which is known as a Nagai synthesis, and it's very easy because he had taken the starting material which is readily available in the market and produce as a high yielding product, and therefore this synthesis is a very useful as far as this. Let us see here first what he did. He has taken as a starting material is this one, CH2, CH3 and NO2, that is a nitroethane. This is known as a nitroethane, and this nitroethane treated with K2CO3 potassium carbonate, which is a weak base, which abstract the proton and form as a carbanion over there, NO2. This is a carbanion, and this carbanion, as we know that this carbanion is a well stabilized due to the resonance, because there is a electron withdrawing group is present. Nitro group is a very powerful electron withdrawing group. It stabilizes the carbanion, and therefore we got in the first. Now in the second case, what is going to happen? Let us, what he did, he had taken as a starting material is a benzaldehyde, C double bond O H, you can write like this, and then this one CH minus charge, then CS3, there the NO2. This carbanion easily attack over there just by hitting. What do you get? You can write over here this one phenyl group, as we know that. Then here CH OH comes over there, then CH NO2, and this one is a CS3. Now this is further treated with reducing reagent SN in presence of HCl. You might be knowing, you are familiar with this reagent. This is a very selective reagent for the conversion of nitro group into as a amine. That is a reduction reaction takes place over there, and you are going to get the compound is this one. In short, I am writing this phenyl is a pH, then CH OH, now CH NH2, and this CS3. Understood this one? That is a primary type of the amine that further treated with methyl iodide, which is readily available. And what the product you are going to get? You are going to get pH, CH OH, then CH NH CS3, and this CS3. Here we are going to get plus minus ephedrine. This one is a plus minus ephedrine. That is the product we are getting. Now is a resolution. Now is a resolution. Why the resolution is necessary here? Because if both the plus and minus ephedrines are present, minus ephedrine has a medicinal property, whereas the plus ephedrine is not useful, and therefore we must resolve it so that you will get as a ephedrine is a pH, then CH-OH, then CH-NH, CS3, this CS3, and which we got as a minus ephedrine, this one. Ephedrine, minus ephedrine is a very, very useful or very, very beneficial to the mankind, because it is associated with the medicinal property, and that's why this Nagai synthesis is very simple. I think with this we have completed as a chapter number 6, The name of the chapter is a natural product. What two part we have divided, we have studied this chapter in two sections. First section we covered, that is a terpenoid. Second one is a alkaloid. So one mark may appear, one mark question may appear in the exam like this: what is terpenoid, what is alkaloid, or explain isoprene rule, state the isoprene rule, or give the special isoprene rule. 1 mark important question, probable question we are discussing over here. What type of the probable question may appear in the exam? So that the list of that question I am discussing over here. So listen carefully. What is alkaloid, or what is terpenoid, or explain isoprene rule, or state isoprene rule, or state the special isoprene rule. So likewise question, or gives classification of the terpenoid, or how will you prove the presence of 2 carbon-carbon double bond in citral, or define special isoprene rule, or how will you prove the presence of secondary alcoholic OH group in ephedrine. Or a question may be like this: how will you prove the presence of aldehyde group in citral? Or 2 or 3 mark question may appear in the exam like this. Write Nagai synthesis of ephedrine. Just now we have seen. Look at on the board. It is very simple. Only 2 steps are there, and all the steps are very simple and easy, so that you can get as a 3 mark. So then give the evidence for presence of aldehyde group in citral, or how will you prove the presence of NaCH3 group in ephedrine, or how will you prove the presence of a secondary alcoholic OH group in ephedrine, or how will you prove the presence of CME and isopropylidine group at 1,4 position in citral, or give the Nagai synthesis of ephedrine, or maybe as a writer notes on IMS degradation, Hofmann exhaustive methylation, von Bondrer Braun degradation. That type of the question may appear in the exam. So I think with this we have covered all the theoretical chapters, whatever is there in your syllabus at T.Y.B.Sc syllabus. Tomorrow onward, remember, tomorrow onward we are going to start very significant, very prominent, or very important, because that is a new topic is introduced at T.Y.B.Sc syllabus, and that is called as a spectroscopy. And that spectroscopy, as far as modern organic chemistry is concerned, synthetic organic chemistry is concerned, it is a very highly important for the research point of view, or even though in a competitive exam it's a very important and a very interesting subject. So that subject we are going to, at that point we are going to start. There are, I think, 4 chapters are there, including how to solve the problem based on those spectroscopy that we will see tomorrow. With this, let us stop today here. Thank you. Have a nice day.